Aquí estoy.
All right, ¿en español o en inglés?
Bueno, de hecho voy a empezar en español, pero luego la charla la voy a hacer en
Ok, ¿sabes
inglés.
qué? Te dejo el espacio, por favor, continúa.
Vale, muy bien, muchas gracias.
Y yo te aviso cuando quede algo así como 1 minuto y medio, ¿está bien?
Vale, muy bien. A ver. Todavía estoy buscando para compartir mi pantalla porque no me sale.
¿Está ahí?
¿Ya está?
Está. Gracias.
Ya
Por
está,
favor,
todo bien.
trata de mantener el tiempo, ¿sí? Gracias.
Sí, claro. Bueno, pues muchas gracias. Claro, como he dicho antes, voy a hacer la presentación en inglés, pero antes de todo quiero agradecer a los organizadores para darme la oportunidad de hacer esta presentación hoy. Realmente es un placer para mí estar aquí. Okay, so I'm going to talk about the use of nanoparticle for multimodal imaging of mostly brain-related pathologies. So, of course, here, when we speak about contrast media, the idea is to enhance the quality of the images. And what kind of imaging modalities are we going to focus on? This is first MRI, magnetic resonance imaging, which is quite complementary with the CT scanner. Both are complementary in terms of resolution, but also in terms of sensitivity. And the third imaging modality we're going to focus on is quite cutting edge. It's 2-photon absorption. It's fluorescence microscopy, which allows to work in a range of wavelengths, as you can see here, that is called the optical window and allows to reach deeper tissues as the classical imaging modality. So here we have a huge resolution and a huge sensitivity. So in order to do that, what we want to propose is to use hybrid nanoparticle consisting in inorganic core based on gadolinium fluoride, and then a biocompatible system, such as a polyethylene glycol, for example. And then around this particle, different kind of dyes to ensure fluorescence or even targeting. So the particles are made by a solvothermal process, just to show you that we react a charge transfer complex, providing the fluoride ions on a complex of lanthanide. And after thermal treatment, we obtain the particle in high yield. So here in the case of gadolinium fluoride, as you can see here in the 10 pictures, we have slightly elongated nanoparticle with a diameter of 9 to 10 nanometers. When we look at the dynamic light scattering, you can see that we have a low polydispersity. And if we zoom in on the particle, you can see here through the high resolution microscopy that we have a crystalline nanoparticle. And this is confirmed with the X-ray diffraction on powder, where we have here high crystallinity with orthorhombic phase. So all those features clearly show that we have great stability for the particles, so no release of gadolinium ions, and systems suitable for bio application due also to the low polydispersity. So what about now the use of this system for imaging? And we look at here at the intrinsic properties, just to show you here for the MRI. You can see that basically here it's the phantom with different tubes filled with suspension of this particle. And here is water. And as we increase the concentration of particle in the tubes, you see that we increase the contrast. Notice that here the contrast is T2 weighted. That is, we have a dark contrast, which is in agreement with the relaxivity measurement that are in the range, let's say, of iron oxide nanoparticles. Now, what about scanner CT? Here you have the same kind of system. That is, you have a phantom filled with different tubes with increasing concentration of the particle. And as you can see here, compared to water, we have here a strong absorption of the X-rays, which can be seen by a white contrast. So here, just to show you here, it shows that the lower threshold is in the same range as the commercially available contrast agent for scanner. So we have something that is suitable for both MRI and CT scanner imaging. So the first example I want to show you of use of this system is stroke. So stroke basically, and more specifically, is stroke is in the brain. That's very important images. And imaging, then the classical the activation through the strong inflammatory process, activation of cells such as microglia, for example, or macrophages. So in order to do that, we want to work with the hybrid nanoparticle. And this hybrid nanoparticle consists in the gadolinium fluoride system. And here, a dye that ensure to work in biological window, both for excitation that will occur in the first window, in the second window, but also for the emission that will occur in the first window. So these particles were prepared through a classical ligand exchange process. So we start with the gadolinium fluoride system. Then we're going to graft around this particle two different kinds of ligands in various proportions. And those ligands are anchored on the particle through these phosphonate units that you have here. And here you can see with the infrared that we can clearly follow this efficient grafting through the appearance of the bond relative to the N3 units, and here to the appearance of the bond of the PO units. So we have first this multifunctional nanoparticle that are further on modified through somehow click chemistry in order to have the dye onto the particles. And this is here a thermally activated click chemistry. So here, as you can see, the fact that the dye is grafted on the particle is not an issue regarding its emission properties, and we keep the emission properties of the dye in a range of wavelength against that is perfectly suitable for bioapplication. So here are the images that we've had after injection of this particle on animal model. That is, we create this ischemic within the brain of mice. And this is before injection with MRI, before injection of the particle. You see here in white the lesion. And after injection of the particle with MRI, you can clearly see here these dark spots corresponding at the presence of the particle within, within the lesion, which is in agreement with the results we've had before, with the fact that this particle is suitable for dark contrast. And if we look with fast contrast on the same brain of the animal, you can clearly see that it's in agreement with previous results, where here we can clearly see the particle in that area as white spot. So here it's interesting because we see the particle are within the lesion, but still we miss some information. And what's interesting with the multimodal agent is that we can go a little bit further into the details and have somehow a multi-scale imaging. And when we look at the peripheral area that we have here, it's the same image here. When we look at the peripheral area here, you can clearly see here in red the bloodstream of the brain, and in red is the presence of the particle. Now, if we look within the lesion, you can clearly see that in that case, here are the blood vessels. They are completely empty of blood, but the particle are within the parenchyma. So here we have something very interesting for multimodal imaging, but also multi-scale imaging in order to see where the particle are located. So the other example, vale, gracias. The other example is Alzheimer's disease, and one of the features of Alzheimer is the presence of amyloid plaque between the nerve cells. And what we want to do is to image this amyloid plaque between the nerve cells. So first, we focused on the use of those systems that are very interesting because they can target the plaque and they can emit light. So we somehow merge the two technologies, that is the particle we design and these LCP units. And we were able to do basically the same kind of imaging as you've seen before, although this time it's more suited for Alzheimer, where when we inject the particle into the brain, you can clearly see here in the healthy area, that is, we don't have any plaque, the particle don't remain. But here, in the case of the, let's say, the area of the brain that was incubated with the plaque, you can see that the particle here are clearly located, and these are the dark spots, because again, we have a dark contrast. And this was confirmed by fast contrast, which is basically scanner CT, where you can clearly see here this white spot corresponding to the presence of the particle. So we did the same with two-photon imaging, where we can clearly see here the ability that the particle can go from the bloodstream into the brain parenchyma, as you can see here, after some time, and we can target specifically the plaque related to the amyloid and Alzheimer's disease. So as a conclusion, we can say that we can somehow design an organic core, and we can tune the size and the composition of the system depending on the modality we want to aim at. We can tailor the system depending on the pathologies we want to aim at, and those systems are a very interesting contrast agent for further use on different kinds of pathologies. So I'd like to thank all the collaborators who helped us during those processes and those projects. I'd like to thank all the sponsors, and I'd like to thank you all for your kind attention. Muchas gracias.